So this topic will be the automobile works with sheet metal. In that, actually, we are going to complete these things. Means we'll see means introduction to sheet metal. In that, we'll see means what is basically sheet metal, shearing operation, bending operations, bend allowances, and spring back. Okay. Then the process design and overview. Means basically what are the major tools actually involved in that case, like the shearing, tearing, the fine blanking, hydroforming, basic guidelines. And in the tool design section, we'll see means types of tool design. Okay. Yes, Rajput, Goman Musafir raised hand. Any you want to say something, Rajput? Okay. As I said, you like please means put some questions in the chat box so that we can later on discuss, right? So that will there will be no interruption during the discussion. Okay. So we'll discuss the various kind of tools being used in the for particular sheet metal. Then we'll see the formability. Okay, and with some case studies. First of all, see introduction to sheet metal. What is sheet metal, right? Sorry. Sheet metal is generally metal which is formed into flat pieces. Okay. Basically, it ranges to 0.2 to 6 mm thickness. Okay. And basically, the below 0.2 is coming with some kind of it's rolling station, and it's a 0.2 to above 6 mm thickness. It will be comes with some sheet metal, and above the 6 mm thickness, it comes with plate. Okay, so these are actually being manufactured in the with cold working conditions. Okay, it's a cold working operations is being formed. The CRC sheets and HRCS sheets. Generally, CRCS is like cold rolled steel sheet, and HRCS is like hot rolled sheets. Okay. Generally, these are actually being the sheet metal is being formed according to the rolling operation, right? So the basically the advantages in this is like sheet metal is generally with high strength. It's malleable in nature. Malleable is in this case like this can be formed into different shapes. That's why it's malleable. Okay. Okay, my voice is breaking. Is it clear right now? Am I audible, guys? Okay, okay. Thank you. Thank you, Simant. So the basic advantages for the sheet metal is like it's a high strength. Okay, malleability in nature. As I told you, means malleable is basically useful for it's a mechanical property for the sheet metal, which is going to useful for the formability. And we can also the dimensional accuracy can be achieved for the sheet metal. The good surface finish and relatively low cost according to is reference to the castings, or it can be like aluminum, and economical mass production definitely. And various of applications being is like used in the automobile sector, aeronautic sector, locomotive, like, and in the car manufacturing, earth moving equipments, even in in the electronic components as well. So various so basic sheet metal operations are actually like it is defined according to the shearing, which is like cutting operations, bending, which is non-cutting, drawing basically means in the form of deep drawing, stress forming, or roll forming, and it is possible with speging, with coining and embossing. Okay, basically in the shearing operation, like in the cutting of any sheet metal, there are various types of tools being used. Okay, still voice is cracking. Okay, sir, sound is not clear. Okay, because of less network issue. Okay, in the shearing category, mostly the cutting, the blanking operation, punching, most of you can say like punching, also called as piercing, trimming, parting off, cutting off, slitting, lancing, notching, perforating, shaving, and nibbling. These are actually comes under cutting operations, right? Well, the shearing sector. In that bending, there are different types of tools like edge bending, V bending, U bending, channel bending, offset bending, rotary bending, hemming, seaming, and curling. Okay. And for the drawing operations like deep drawing, stretch forming, roll forming, and squeezing, already told you, the coining and embossing. So there are various types of tools can be performed, and various types of component can be performed by using of these kind of tools. Okay. So it's really going to be, practically you have to think like, means what are the different kind of operations being performed, means what are the components we have. So every possibilities can be occurred with the kind of in the form of sheet metal. So we'll see, means in brief, means what are the different types of operations in the sheet metal. So basically shearing is like the basic is like the first one is the blanking and punching as piercing. The blanking operation is like it's a piece of sheet metal is removed from the large piece of stock called as a blank. Okay, blank can be in the form of strips, right? As I told you, means the sheet metal is with in the rolling feature, so that can be in the strip or it can be a blank. And punching operation is similar to blanking, except the cut piece is a scrap. So here you can see the basic difference in the blanking and piercing is this is the actually blank part, this is going to be scrap. Okay, here this is the strip, the cut piece is here is the part. Here after the blanking operation, the slug is being taken out, means this is the piercing. It's a hole is important here, the outside is important. Okay, so this is the blanking operation and this is the piercing operation. Okay, and there are various types of in the blanking and punching, like means for any cutting operation, right? There are means these are actually basic stages in the during the process. So first is like the strip is being contact with the punch. Okay, then the elastic and plastic deformation will carried out. Then actually shearing and crack information will be taken care. Then it will completely fractured. Then the component will be stripped out. So these are actually basic stages during the any blanking or punching operations. So these are actually various examples for the particular operations. Okay. Like trimming generally means after the deep drawing operations, there are some kind of means non-required areas which is need to be cutting, that is comes under trimming. Okay. Then parting off is generally to cut off the different jobs. Okay, and the cutoff is the same kind of operations, but the difference is here the parting is generally defined, means the part is generally there are two consecutive parts being part of. Okay, but the cutoff is like we have to create different the strips will be cut off according to the punch. Okay, and the slitting is like to at least to give us little cut, it comes under slitting. Lancing is like okay, sound problem, still having sound problem. Okay, actually means I can't do on this. It's a sound of breaking or it's completely not audible. Okay, because of network only. Okay, I can't do much on this. Okay, we'll see. Once little bit slow, we'll go with. Okay, then the lancing operation. Lancing is generally generally operation is like three means the completely part will be not cut. Only 2 or 3 edges will be cut in this case. Okay. Then notching. Notching is like it can be a V notching, or it can be square notching, or it can be any shape. It's given particularly the edge of the component. Okay. Then perforating. Perforating is basically explaining to the piercing punch. Okay, means in the sheet metal there are number of holes can be perforated into small holes. Okay, so this comes under perforating. So it can be sheet metal, or it can be like in the form of tube as well. Okay, and shaving is like so fine blanking, right? Means the very less amount of edges are being removed from the outer edges. And nibbling is like means make some kind of specific features at the edges is performed under nibbling. Okay, you can see over here these are various little bit of cutouts. Okay, and this is very difficult to make some kind of means a punch. It will means specific round shaped punches are being performed in this case. Means various strikes can be given to the edges of the component so that some kind of features can be performed. And these are actually some actual components which are being used in the industries. Okay, slitting is like directly to slit the sheet metal. Is slitting is like a kind of, okay, and in this case there are cutting rollers are there which actually slit the sheet metal. And trimming is like, as I told you, like this is actually plus fuel tank top cover, right? This one. And after drawing, there are some kind of unwanted sheets which is need to be removed. In that case, this is the operation is like trimming. Okay. And notching, as I told you, some basic shapes. It can be V, or it can be square, or any kind of profile given to the edges of the component. Okay. Then perforating, as I told you, this can be a circular shape, or it can be any shape which are being performed. In the perforating itself, only single piercing punch can be used. Only the sheet metal will be removed according to the means moved according to the requirement. Okay, it's actually continuous process. The perforating process is a continuous process where it can be like CNC, or it can be numerical controlled. Okay, means the single punch can be used at multiple times to make these kind of profiles. Okay, or shapes. In the lancing, I told you, only 2 sides of edge of cutting, or it can be 3 sides of cutting. And nibbling is like, as I told you, means some kind of specific feature is required in the edge of the component. Then in that case, the nibbling process is taken care. And the shaving is like the fine blanking, where the outer shape is very much of important. We'll see means more in that particular the shaving and fine blanking operation in the later on in more depth. Okay. And for the non-cutting tools, which is like edge bending. Okay, edge bending is like the sheet metal can be bent at the edge of the part. Okay, here you can see this is the process. The pressure pad is being means the completely the force will be okay. Now the pressure pad is at least receiving the force to hold the workpiece. Then some wiping die will become, and this will bend by the actuating force. Okay. Same of V bending. This is called the V. There is some V punch is used, and V die is used for the V bending. And then U bend. It's like a U shape only. And channel bending, the channel is like it can be means a rectangle channel, or it can be some kind of different shape of channels. And offset bending is like 2 bendings can be possible in the single sheet. Okay, it can be offset. And rotary bending, in this case, this is the rotary punch. It will rotate according to the force. Okay, the rotary action also be being performed according to the requirement. And hemming is like to hem the edges. Okay, we'll see the different kind of this is generally used to given the strengthen the edges. Okay, the hemming process is used for the strengthening the edges. Then seaming is like means 2 sheet metals can be assembled by the seaming operation. And curling is like the same operation like with hemming. It is also used for the strengthening the edges. Okay, so hemming is completely striking of the two edges. Here curling, in this case it will curl a little bit. So these are some kind of actual components. Okay, this is the edge bending, only the edge is being performed. The V bending components like this, and we can see the U bending, only the U shape particularly. And channel bending is like it's kind of, you can see the right angle channels. Okay, and offset bending. Okay, there are two bends, right? This one and this one, two bendings. And rotary bending is like, you can see this punch will rotate according to the edge of this sheet. And hemming is given for the edge of the component. Okay, and seaming is like I told you, means to assemble the two components. Then this can be possible in the seaming operation. And curling, this is the curling. Okay, I will just curl the edges. Okay, now we'll see the bend allowances. Okay, actually the bend allowance and the spring back. This is actually two common things to know before any bending operation. Okay, because these are actually basic things which are generally occurs during bending. Okay, so bend allowances like means how much bend means the completely the flat blank length, because means the distances need to be calculated according to the bend allowances. Okay, here you can see this is actually bend allowance. Okay, and bend allowances, actually this is the arc length of the bend along with the neutral surface of the material. Here then this is the actually neutral surface, you can see. So this length must be calculated in the properly while doing the bending process. So this is actually basic formula. Here the bending allowance is like alpha is the bend angle, pi we know 3.141 divided by 180, and R is like the inside radius of the component. Okay, and K is the safety factor. Okay, safety factor in the sense like it's depend on the inner thickness of T up to T, the overall thickness of the component. So generally it is like the thumb rule of this calculating K factor is like if the inner radius is less than 2 times of thickness, then the K must be 0.33. Okay, this is the thumb rule which we are using in the while designing of any bending tool. Okay, and if that radius is greater than 2 times of the thickness, then the K must be 0.5. Okay, let's example like if the sheet thickness is 2 mm and the inner radius is like 4 mm, then the K must be 0.5. And if the sheet thickness is 2 and the inner radius is 3, then the K must be 0.33. Okay, so these are actually basic rule need to be followed while designing. And this is some kind of examples how to calculate the pre-bend length of the blank. Okay, here you can see this is actually this is the blank. Okay, and the dimension has been given. Okay, you can see, and here is already telling like you have to keep that K must be 0.44. Okay, so in this case you can see like these are actually various lengths. We are generally means a flat length and some kind of angular length we have to calculate. In this case L11, which is bend allowances, and this is L12 and L13. Okay, and you can see over here this is given R5 only. Okay, here see this is actually radius 5, this is the outer. But in this case we have to think like means the question will be like we have to consider only the inner radius, not the outer. Okay, so if the thickness is like 2 mm and the radius will be the 5, then the by default radius will come, it will be 3 only. Okay, so here you can see the R1, R2 and R3 will be 3 mm. Okay, the radius, outer the radius and the sheet thickness. So this will be 3 mm. Then the L1 is 116 minus 5 because the total length is given is 116. So we have to reduce the length of this radius 5. So it will reduce by 5. So it will be L1 will be 111. And L2 is already given 75. And L3 also given how much? it's a 75, and L4 is 40 mm. Okay. And here the point to be noted, like this is actually 90 degree. Here the bend angle is 90 degree. And here you can see this will be 72 degree. Okay. So this degree will be 108. You have to calculate because this is 12 degree. Okay. 72 degree means it's 18 degree. So 90 plus 18, it's a 108 degree. So according to the formula, we have to calculate like L1, LN1, LN2, LN, LN3. Then we have to addition of all this length, it is to be the total flat blank length. Okay. So whenever the components comes like this, we have to calculate manually, or some kind of formulas are there, means some automated softwares are there, means how to calculate the total flat blank length. Even in the CATIA and different softwares are also is coming with some kind of options. We can define the total flat blank length. Okay. Now we'll see the spring back. As I told you, means bend allowances and spring backs are actually two major factors to be considered while designing. So spring back is like this is actually elastic stress which is remaining in the bend area after bending the pressure released. Okay, means after the operations being performed, this will move to some kind of original position after the operation, particularly the bending. So it will deflect little bit. Means how much it will deflect, we have to calculate. Okay, and here you can see this is the actually initial position while the bending operation. Means after the releasing of the component, this will go a little bit of to its original size. Okay, so it will deviate from the original. So this is called spring back. Means how much is spring back? It is depends totally on the metal properties. You can see say like mostly in the case of young means how much is the elastic in nature of the component. Okay, like it depends on the modulus of elasticity, it depends on the elongation criteria. So these things are actually considered in the specifically in the spring back estimation. So basically the spring back estimation formula is like Ri by Rf. Ri is like initial radius divided by the final radius. Means how much radius is being means after you have to inspect the total radius of initially how much is we given in the design and the final how it came. So this is actually spring back estimation, and the formula is like Ri and Y divided by ET. ET is like it's elongation ratio, and Y is the Young's modulus. Okay, so this is the formula we have to calculate according to the, and Young's modulus and elasticity of this component is according to the sheet metal. So this is being given in the metal itself, metal chart itself. So we have to calculate only means we need to identify means how much Ri and Rf which is being inspected and which is given in the design itself. And after that, we have to calculate the total spring back factor. Okay, so I'll move on. We'll see the first thing actually we completed means the introduction part about the different kind of tools being used, or different types of components can be performed in the various tools. That can be, it can be like shearing, or it can be like bending. Okay, now we'll see the overall process and design overview. Okay, means how the parts can be designed, the different types of tools can be designed. Okay, first of all, see means the shearing or cutting. Okay, shearing and tearing is taking place during the cutting operation. Okay, during the cutting operation, there are different forms can be comes during the process. Like this is actually during the cutting process, there are various things like 1 over is rollover depth, then it will little bit of burnish the edges, then it will fracture, then there also be possibility of some kind of burr height. Okay, generally these things will occur during the process, and the dimension of each and everything this to be factored according to the sheet metal, also according to the clearance we are giving. And because the why the clearance is being taken care here, because of the operation only, means if you are considering the blacking, and let's say blanking, or let's say it's a fine blanking. So the clearance will be different. So according to the clearance, this burnishing depth will depends. Also the fracture. So mostly in the sheet metal for the blanking operation, this fracture depth is always 2/3 of the sheet metal. Okay, and the burnishing depth will be 1/3. So this is actually basic principle of the cutting of any sheet metal. Okay, means 1/3 of this will cut, then 2/3 will be fracture. Okay. So during the process, the elastic compression on the top side, here you can see only the elastic deformation will be in the top side only, and elastic elongation will be the bottom side. So during the compression, while the punching will be taken care, then there will be some compression at the top and elongation at the bottom. And after the completely forces given to the part, the fracture will occur. Okay. So basically in the punching operation, as I told you, it's completely depend on the clearance we are providing. So generally the basic rule for the punching operation is like the punch size is always the hole size. Okay. And the clearance is given to the die only in the piercing tool, and shear will be happen to the punch only, not in the die, because the punch size is the critical one, and in the die itself the clearance being given. And the same in this case, you can see the component in the piercing, you can see the shearing will be done, means the total burnishing will be done at the top. Okay, and the fracture will be at the bottom in the piercing. But the same in the die, you can see the actual cutting, means the burnishing will be at the bottom and the fracture will be at the top of the thickness. So this is actually basic difference we can see in the blanking and piercing. So anyone can see in the, means if you are having some components, then you have to decide according to by looking at the component only, means whether it's a piercing or blanking. Okay. Now we'll see the fine blanking process. Okay. The fine blanking process, some high pressure pads and which are being used to prevent for the metal. Generally, while properly, it will hold the sheet with some kind of high pressure pads. Okay, and in the pressure pads also there are some rings or grooves can be provided, so that the area of this sheet will be completely gripped. Okay, and also the clearance to the die, or it can be punch, is given only 1% of the sheet thickness. Okay, generally the thing is like particularly in the blanking and piercing, mostly the clearance is defined according to the sheet thickness, also the operations performed. Okay, as I told you before. Now in the blanking operation, the 1% of the sheet thickness is the proper calculation, and in the blanking and piercing, it can be vary according to the number of components can be manufactured. Okay, so it's basically ranges from 4% to 15%. Okay, the clearance of the clearance given to the die or punch will be like 4% to 15% of the sheet thickness. But in the fine blanking process, it reduces to 1% of sheet thickness. Okay, this is actually generally thumb rules. Okay, so in the blanking process, like in this case, we'll discuss about in detail, like the tool in the open condition will long with the strip ready to be cut. Okay, then the bottom moves up and the tool closed. Means while during the process, there will be some ring grooved, as I told you here. The ring will be grooved and the counter force will be activated. So means this plate has some grooves which will completely grip the sheet metal. Okay, so this will not deform any further to the component. So the sheets can be properly gripped and clamped. Okay. So then the blanking force is activated and metal being cut off to the part. Okay, and ring groove and counter force will be remain still active in this case. Means during the process itself, you can see over here, this is the actually component and this is the ring. It is completely intact during the process. Okay. So it's a completely hold a sheet metal during the process. Then the bottom moves down and tool will open condition, means ejector force will be activated and the slug will. So the basic difference in the blanking and fine blanking is the extra plate being given for the holding of the component. Okay. And the sheet clearance means the die clearance is about to only 1% of the sheet thickness. Okay. So why blank means why will providing some fine blanking? Okay. These are actually like the basic advantage of measuring means manufacturing of any auto components. These are actually some kind of auto components being used for the fine blanking process. We are actually manufacturing some kind of levers, okay, in the automatic braking system. Some where even some gears manufacturing also possible. Like we can produce some kind of sprockets. Generally, cam sprockets are manufactured through fine blanking, okay. And cam sprockets are like you can see in the two-wheeler industry. The cam sprocket is generally used for the chain transmission, okay. The timing chain is actually being guided with some camshaft, okay. So these are actually some kind of examples being manufactured through fine blanking process. And as I told you, some kind of advantages like this is a high precision. Definitely the close dimension tolerance can be achieved. And mostly produce flat edges because you can see in the basic conventional stamping or blanking procedure, there is no stripping forces being given for the holding of the component, okay. So in that case, what will happen? The metal will deform a little bit, and even the component also will deform a little bit. So, but in the fine blanking, there are some counter punches being given, which is a kind of spring loaded, okay, so that the completely force will be given the both way. Here you can see this is completely idle, the below. So this part can be deformed, but here it is not possible. Okay, so it will definitely will give some definitely flat edges and having little or no fracture zones. There will be no fracture zone. As I told you, the clearance is very much of less in this case, and only the cutting process will be happen. You can see the fine blanking part. You can see only the sharp edges, right? Here you can see little bit of cutting, then fracture. You can see the conventional blanking. Okay, 1/3 of the sheet metal is the cutting, and 2/3 of them will be fracture. Okay, so post-processing operations such as shaving, deburring, grinding, and milling can be definitely eliminated. Okay, so these are actually useful to avoiding such kind of operations. Means post operations can be removed as well. But there are some limitations as well in the fine blanking, like these are really expensive as compared to other tools. Okay, so this is also very expensive during the long run times. Okay, so we have to choose wisely while going with the fine blanking process. Okay, the next process is like the hydroforming. Okay, mostly these are actually commonly used for the forming process, which are actually quite impossible for the traditional tooling. Okay, a traditional tooling means like for any kind of V bending, U bending, or it can be some kind of deep drawing or anything. So this is apart from the traditional process. Okay, so basically it's a cost effective and specialized type of die molding that utilize high pressurized fluid to form the material. Okay, so there are two types can be used. Some kind of basic the die mold can be designed in such a way that will put that part means tube in that shape. Some kind of pressurized fluid can be given, okay, so that it will form the shape. Okay, so in the form of tubes, there are according to this is also defined in the different tools. Like this can be sheet. Okay, in that case of sheet, we have to use some kind of rubber diaphragm forming. Okay, here you can see this is the rubber diaphragm framing where the sheet metal can be placed over here, and we have to give some injection channel where that fluid can be pressurized to the sheet metal, and later on it will form the shape. Okay, definitely there must be a sealing is required so that there will be no leakage during the process. And even the tube itself, okay, like this is used for low pressure hydroforming. Even high pressure is also definitely possible. And it is also possible some kind of variational of some kind of sequence of process that can be given, like a sequence of process in the sense like we can achieve different types of sections in the same tube. Okay, we'll discuss more later on. So here you can see the hydroforming procedure. There are two dies. In this case, the first the tube will be placed. Okay, then the closing of the mold. Then we have to fill the component with some kind of fluid. The axial feeding is given. Okay, then some kind of fluid is given with high pressure, so that the form will create, and the form will take the shape according to the shape given to the mold itself. Then the component will be removed. Now we'll see in detail, means the low pressure and high pressure hydroforming. Generally, high pressurized hydroforming can be achieved for the tubular, or can be some kind of rectangular cross section. Here you can see there are two dies, two halves, where this tube can be placed. Then after, means even by using the sheet, round shape, it can be formed to the rectangular one. Okay, so this is achievable in the high pressure. Okay, but in the low pressure, definitely is possible, but it will not form in that intact in the low pressure. So this is actually basic difference. And mostly the low pressure, in the low pressure hydroforming, the pressure is around 820 bar, and cycle is in the high pressure hydroforming. And as I told you, in the high pressure hydroforming, the cross section periphery can vary, right? Means we can achieve different types of cross section at various stages. And here the fluid pressures are between 1380 bar to 6900 bar. Okay, so basically this can be used for the longer cycle runs, and the most of the components like the plumbing fittings, bicycle frames. So you can see the bicycle frames, right? This is being performed through hydroforming only. Okay, so even in the pressure sequencing hydroforming, where wall thinning does not occur. Okay, means wall thinning is not possible in this case, and internal pressure is 7000 psi, is 4400 bar, and mostly the automatic structural parts being considered in the pressure sequencing hydroforming. Okay, and this is already told you in the for the sheet metal parts generally. Okay, so there is some rubber diaphragm is used to intact the pressure. Also, there's some kind of a pressurized fluid is being given, and the final shape will be completed to the removing in the punch. The means that rubber diaphragm. Okay. Now this is actually we have done in our shop. Okay, some kind of engine bracket. Okay, this is actually given for the scooter. Okay, and we have produced this engine bracket in the hydroforming tool. Okay, means this is actually some kind of add-on parts actually we have added later on, but this is actually tool. Okay, this is actually channel completely machined, and some after that putting that pipe kind of this part will be manufactured. So in comparison to the conventional construction, this is definitely the 30% lower to the weight. Okay, 20% lower cost, and 60% lower to the overall tool cost. Okay, so definitely there are some more advantages as compared to the traditional forming. Okay, so other advantages in the tube of hydroforming is like optimized section geometry and work hardening. Okay, means section geometry, as I told you, various sections can be performed. So which is not possible in the traditional die design. Okay, and tight tolerance and reduced spring back. Here the spring back is very less because of the completely pressurized fluid is being given. So there will be very less kind of spring back, and tight tolerance also can be achieved. Reduce scrap since minimum timing. Okay, because of this is also reduce the scrap level, because there is no such kind of trimming is required after the drawing itself. So definitely there will be some scrap advantage, and better sound and vibration dampening due to improved stiffness. So there will be no thinning is possible in the hydroforming. Okay, so which is actually generally considered during the drawing itself. There must be some thinning is coming, right? The means during the drawing process, the sheet will be thinned a little bit, but in the form of hydroforming, there will be no thinning. So definitely it will improve the stiffness of the component, because the overall thickness will be same overall the component. Okay, the deep drawing ratio can be increased. Okay, so we can also the part can be deep drawed. Okay, and very complicated specimens can be also possible to manufacture. And the outer surface of the specimen is free from the defects. As I told you, this is being performed in the die surface, so there will be no some kind of defects can be produced during the process. Okay, so these are actually some kind of basic examples we are generally performed during the hydroforming. Okay, these are some kind of engine frames. These are actually used. Okay, this is actually frame of the scooter. Okay, some kind of even this shapes will be possible. Okay, you can see different kinds of arms, various shapes you can see. Okay, so these are actually some useful components during in the automotive components. Even these are so kind of, you can see various shapes will also be possible in the hydroforming. Okay. You can see over here this component, which is really difficult in the form of any process, in the traditional process. So this is very effective in the hydroforming, right? Now we'll see some basic sheet metal design guidelines. Okay, means during the any design procedure, some basic practical experience. Actually, I'm just providing some here. Like if the sheet thickness is let's say T, then the edges must be at least 1.5 times to 2 times of the sheet thickness. Okay, this is not advisable. Okay, if you are going to pierce some hole, then the edge must be at least 1.5 or 2 times of the sheet thickness. Okay, and for the bending, this must be at least the height of this bend must be at least 1.5 times of the sheet thickness. Okay, and between the two piercing holes, this must be 2T or 3 times of the sheet thickness. It should not be less than the sheet thickness. Okay, this is some basic guidelines to be considered during the designing process. Okay, it's a part development, part design only, not the die design. Okay, this is actually guidelines for the part design. Okay, and let's say like if the sheet thickness is let's say 5 mm, then the piercing hole should not be less than 5 mm. Okay, and it must be 2 times of the sheet thickness or greater, so that the proper shearing or bending can be possible. Okay, these are actually basic guidelines. And for the notching operation, here you can see this is the notching operation, where A must be greater than or equal to metal thickness or 1 mm. Okay, means let's say the sheet thickness is 0.5, then it must be 1 mm in that case. Okay, and whichever is greater, means if the sheet thickness is let's say 2 mm, it must be equal to greater than or equal to 2 mm or 1 mm. So in that case, we have to consider the 2 mm only, and the dimension of B must be less than 5 times of A. So in the notching cases, this is actually basic things. And for the tabs also, the A must be greater than or equal to 2 times of sheet thickness, or it must be at least 3.2 mm minimum is required. And the B is also, it must be less than the 5 times of A. Okay. And some kind of basic sheet metal design guidelines. In this case, you can see this is some kind of actually components we are manufactured. Like there is some kind of collars can be given to the sheet metal so that it will increase the stiffness. Okay. So here we are not going to add some kind of bushes over there and do the welding process. This can be achievable in the form of collar to just draw with the use of draw tools. Okay. And some kind of coining and embossing also given to strengthen the hole. Okay, you can see. And be wherever the long components you can see, there must be the edges must be bent so that there will be no cracks, or it will definitely helpful to give more strength to the part, okay, by only giving some kind of bends to the edges. Okay, you can see little bit of bending is given. Okay, also there we can also give some kind of beads or chamfer at the corner. Okay, so it will also increase the strength of the component. Okay, okay, so we'll move on. Now we'll see the basic tool design. Okay, as of now, actually, we have seen like some basic guidelines, various types of tools according to the cutting, non-cutting, and drawing, and some basic clearances part we have already taken care. Some bending allowances, spring bags. Now we'll see the tool design. Okay, but in that case, we'll see mostly the press tools, different types of progressive tools, compound tool, and we'll see one case study. Okay. Generally, the product development life cycle of any tool design or any part design, we have the basic cycle is defined in the 5 stages only. First, the product design, then the process planning, how that part can be planned and manufactured. Then we'll do the tool design, then the die manufacturing, then the last one is tool trial. So we have we'll go a little depth in this case. Like in the product design case, let's say means after the tool trial got failed, then there will be 4 cycles being taken care, which is going to be a huge loss in this case. If the product is failed, then which is identified as tool trial only, then there will be a huge loss because of these 4 cycles has been already completed. Okay, so product failure is really a great failure to incur the more loss. And if it is failed in the planning phase, then definitely the 3 cycles will be lost. So it is always preferable. Like, so in the product design itself, it must be controlled in such a way that it should not fail during the trial itself. Okay. So these things will be considered during the any tool or component design. Okay, as I told you, means these are some kind of basic things you have to think any kind of product design. Okay, for specifically in the sheet metal part. So try to avoid these kind of mistakes, as I told you before, to fail at the end. Okay, even those limitations can be also eliminated during the process of during the process planning also. So in the tool design, definitely is possible to at least to avoid those things, but it is always advisable to eliminate those errors during the product design itself. Okay, to eliminate the major cost. Now we'll see the type of press tools. Press tools are actually basically depends on the operations. Okay, and the set of operations. Okay, in the best of operation means only one operation. Okay, and if there are number of operations, then it is also different. So based on single operations can be like blanking, punching, and piercing, trimming, shaving. It can be forming or drawing, or it can be deep drawing, bending, assembly tool, and fine blanking tool. This is actually only one operation can be performed during the operation. Okay, any particular stroke. And the based on set of operations, like it can be single operation tool, or it can be compound, combination, or progressive. So multi-stage operations can be performed during the in the set of operations. Okay, so we'll go in detail. So first one is like progressive tool. Okay, and this can be performed during the with a progressive tool. Okay, the progressive tool is like it's a multi-stage tool. In each stroke, all stages are executed. Okay, so means there are total 7 stages where all the strokes are being performed during the each stroke. Okay, so we'll see a little bit in depth. Like the first process is like, let's say this is the strip and this is the stripper guide where the sheet metal will be guided throughout the process. Okay, then there is one piercing pilot hole which is being performed during the piercing. Okay, this is also need to be piloted. Then the second process will be the punching. Here you can see the punching operation of this profile. Then at that time, the piercing operation which is performed earlier, that will be located during the punching operation. Here you can see the piloting. Okay, the piloting and punching will be taken care of the same time. Okay, then the third process will be the punching. Here you can see the punching operation of this outer edges and this as well. So both the edges will be cut out. Then the fourth operation will be here the bending operation. Okay. The fifth one will be here the outer bending. Here one bending will be here. Second one will be here. Then again the piloting operation means every time the part can be piloted. Okay. Now at the end of the components, the final stage will be the parting. So that there will be a parting tool where this part can be separated from the strips. Okay, means for each stroke, there are total 7 stages being performed in each stroke. So during every stroke, these operations are being performed in the single stroke only. Okay. So this is actually continuous in the feed movement. There will be some kind of automation given to the procedure during the strip movement. So it will be a continuous process. Means for each stroke, the one component will be carried out. Now we'll see the compound tool. Okay. Compound tool is like where 2 or more cutting operations being performed at the same stage with a single stroke only. Okay. The basic difference is like the progressive and compound is progressive. You can see only single operations being performed during the each stroke, right? But here you can see the particular one stroke, there will be inner cutting and outer cutting as well. Okay, you can see for this washer. Okay, you can see the washer here you can see the die blank, where the outer edges will be cut. Okay, and this is the stripper, and this is the punch for this die, and this is the punch for the piercing hole. Okay, so while giving the stroke itself, you can see while giving the force itself, it will cut over here. Okay, the outer will be cut and the inner will be cut, and the piercing punch is being guided with the spring loaded. So that means after the cutting process, okay, it will eject the component to the scrap as well. And this is the stripper pressure pad is being given to hold the component in firmly way. Okay, so and remember one thing during the compound die, don't do mistake like putting some kind of punch to the top. Just remember one thing, the die blank must be at the top only. Means if the outer cutting is there, then that will be at the top end only. Why it is? Because I've just made one mistake over here to give you the more insight. If we put the punch at the top level, then the piercing will be done at the bottom. The scrap will stuck over here only. It will not move to the upward. So it must be go downward only. The scrap must be removed at the bottom only, right? So it is some basic things needs to be taken care while designing of some compound tools. So don't do in this way. The piercing punch must be at the top only, right? The piercing punch must be the top side only. Okay. So already seen these things, the compound tool. And now we'll see the combination tool. Okay, combination tool is like in the single stroke, we can use 2 kind of operations. Okay, this is kind of, we can say this kind of progressive, but it's a little bit different to the combination. Combination is like what we'll do first a blanking operation. The same time, this blank can be placed over here. Okay, and the bending can be performed. You can see over here this example. First, we'll cut out the outer shape of this component, the blanking operation. Then this blank will be placed over here, and some kind of drawing or any kind of bending can be possible in the process. So with the same stroke, 2 operations can be performed. Okay, so this is a combination tool, combination of blanking and forming. Okay, now we'll see various difference between the progressive, compound, and combination. So the progressive is like it's a multi-stage tool. Definitely, it's a multi-stage already seen in that previous example. And single or multiple cutting and non-cutting operations at any stage, right? So single operation or multiple cutting or even non-cutting also possible in the single stage only. And in the compound tool, you can see only single tool only, and two or more cutting operations in the single stage, right? Two or more cutting operations can be possible in the single tool. And it's a combination tool. It's also a single stage tool, but there are two combinations can be provided. It can be blanking or it can be bending or drawing, right? And specifically differentiate in the feature. Definitely, this progressive tool is very effective, very productive, and the utilization of strip is very much utilized in the production progressive tool, and less dimensional accuracy due to multiple stages. Okay, here you can see the basic disadvantages like dimensional accuracy is very less. Okay, because of multiple stages are taken care. Okay, but in the same thing like in the feature of compound tool, productive must be less than the progressive tool. It's not as good as progressive, but definitely it's productive. It's a better stipulation as compared to progressive tool, because here you can see there is no specific scrap and only the outer and inner is being performed, so that it's a definitely better stipulation as compared to progressive. And good dimensional accuracy in the form of blanking and punching can be in a single stroke. So more accuracy can be achieved in the compound tool. And same in the combination tool, it's definitely productive, but it's less than the progressive tool. And here is also it can be better utilized, the total strip layout, and good dimensional accuracy can be possible in the combination tool as well. Okay. Now we'll see on case studies what we have did in our component manufacturing. This is actually some stay evapo, right? And these are actually various operations being considered for the manufacturing of this part, like the blanking, these are piercing, these are stamping, and embossing, and bending as well. Okay, these are actually various stages been considered during the manufacturing of this evapo. Okay, stay. So here we have considered like we have not directly jumped into the blanking or piercing operation, that we have skipped for the trial purpose with some kind of laser cut blank. Okay, so directly we are not jumping to the blanking and piercing. We have taken care of the blanking as a through laser cut only. Okay, so that also can be done with the blanking and piercing, but we have taken in the laser cut to save some kind of money in the trial itself. So then the total sequence of operation is like blanking, piercing, the bending and embossing in the same tool, and the final part. Okay, so these are actually basic 4 stages being performed during the manufacturing of this stay evapo. Now we'll see one by one. First, during the blanking process, we have to analyze the strip utilization. Okay, this is the first stage, how the blanks can be effectively put in such a way that so that the strips will be more effectively utilized. Okay, here you can see this is the actual direction of the component being placed. Okay, these are the 2 proposals we can see, and in this case the sheet thickness is the same, 1.6. The gross weight of the strip is 42 kg, 42 gram of this component, and net weight for the one component is, let's say, 22 gram. Okay, and here the utilization of is only 53%. Okay, and rest of the area will be as a scrap only. Okay, but here in this proposal, you can see the gross weight of the one in stroke is 63, right? And you can see the total gross stroke here. So 2 parts can be performed, like, so you can see the 70% of the utilization. So it is a multiplication. The utilization is like area utilized by total area. You can see it will be divided by 44 divided by 63 is 70%, and here the 22 by 42 is 53%. So which is preferred is a proposal 2. Okay, so the for the blanking operation, this strip layout is taken care. Now the piercing operation, after the blanking, we have to place the component in such a way that they'll be properly located, and the 2 piercing holes can be performed during the process. Okay, so this is the basic tool for this piercing operation. Okay, now we'll see for the embossing and bending. You can see there are 2 locates being given in the as a locator for the piercing. We already did that before, and there are some spring-loaded ejector blocks are given, at least to stripping out the component after bending. Okay, so this is the punch in the yellow color, and during the process, after completion of the process, during the spring load, it will remove the component by ejecting from the this ejected block. Okay, this is the actually final product. Okay. Now we'll go with in deep, like how much clearance is given to the particular means any punch or die. As I told you earlier, like in blanking, clearance is provided in the punch, in the piercing, clearance is provided in the die. But in the sharing operation, the clearance must be close edge, because otherwise it will create some kind of burr or any kind of it will not cut easily. So, and generally the stresses being actually, this is strips, and some kind of stresses being released after the blanking, and some kind of in the piercing as well, there are some outer thrust and some kind of you can say that in the tensile stress is separated from the part during the blanking process, and in the piercing there are some compressive stresses being generally generated, which is separated from the piercing. Okay. Now we'll see the formability. Okay, means what is formability, and what is the forming limit diagram, and so we'll do some kind of investigation. We'll go with some example actually we did for the fuel tank inner. Okay, tank outer, and the fuel tank inner. Okay, for the two-wheeler. We'll see means basic things for the formability and from the case studies for point of view. Formability diagram generally used to understand means how the sheet metal is going to perform during the drawing process. Okay, so various aspects like how much is going to be stretch, right? How much it will wrinkle, the wrinkling tendency, that must be some kind of excessive thinning. Okay, so these are actually basic things, and needs to be considered during the forming process. So there is some kind of forming limit diagram is there, where we can understand where the various sections can be analyzed properly, so that we can avoid those mistakes while making such kind of products. Okay, so formability is like this is the ease with the which where metal can be shaped through plastic deformation without a failure, right? Formability is like as I told you, sheet metals are generally malleable in nature, so it can be formed easily into any shapes. Okay, so this is actually formability nature for the particular part. So where the plastic deformation can be taken care without any failure. So involvement measurement of any amount of deformation required to the cause fracture, right? Means as I told you, means we have to analyze through failure forming limit diagram where the sheet metal can fracture and where the plastic deformation can be easily possible, so that the thinning will not be as much as, so that it will create some cracks or a kind of any failure. So generally, FLD diagram is developed by Keeler and Goodwin. So, and simply it's a plot of the major strains against the minor strains. Okay, means we'll discuss more in that. Means what is the major strain and the minor strains, specifically on during the process. Okay. So forming limit indicate the limiting strains that sheet metals can sustain. Okay, these are some as I told you by analyzing these conditions. Actually, this is actually in the form of FLD, where the form is actually some kind of software where we are using for understanding for the particular where the forming can be done, right? So forming limit diagrams is like it's a procedure where the sheet metal is being marked with some kind of circles, grid of circles. You can see over here, there are a number of circles being gridded. Then the blank is stretched over a punch until the grid patterns deform where necking and tearing occur. So we are going to stretch those part with some kind of punch until it will deform and tear, right? So in that case, we'll see the deformed circles are measured in the failed region where that some kind of failure is produced. So we are going to understand what is the major strain and minor strain. So major strain is like how much is actually axially towards x and y, right? Means how much is it going to be upward and downward, right? It's a bunch of strain and stress. Okay. So in that case, we have to consider at least typically 10 data points over here, means the number of points where we are considering for the FLD diagram. So a series of tests can be settled metal procedure of FLD. So number of procedures can be being followed to understand the FLD diagram. So here we can see in the example, only the let's say 4 mm diameter is being drawn in the sheet metal. Means after punching, the major ellipse axis is happened like 5 mm to 3.2 mm. So in that case, the major strain will be 25% and strain will be minus 20%. Okay. So according to that, means these are actually serious thinning areas. We can understand where it is going to be deformed or it can be stretched. Okay. So basically it represents in the autoform surface, right? So before any drawing or any forming, so we are analyzing these things in the autoform so that it will be easily to give the analysis before any making any decisions. Okay. So these are some kind of inputs which we have considered during the process. Like we have considered in the CAD form in the .MATLAB or it's a mat form. Okay. Then the Automotive software, then it will generate where some kind of error can be analyzed. Okay. So after evaluation of this fuel tank, this is actually process where the process part can be manufactured. Like first one is the blanking, then drawing, then cam trim piers, and the last one is the cam form piers. Okay, these are actually 4 stages for the making of this particular fuel tank inner. Okay. In the autoform feature, we can see here like various sections where it is going to be create some kind of thinning or fracture. Okay. So here the condition is for this is like metal we have taken is EDD, thickness is 0.8, and we have used for the as a lubricating oil let's see of 0.15, and the tonnage is equal to 30 ton. So here in the autoform feature, after and before trial, right, where thinning is result, here we can see as a 0.21. Okay, this is actually practically we did in this software, and also we have manufactured this component. And there are some visual thinning where the software gave some kind of results during the process in the autoform. Then after the manufacturing, these are the actual thinning, right? Means where the part got thinned. Okay, and there are also some kind of rules, means how much thinning is acceptable and not acceptable. So here different means percentage. Okay. So just hold on. So these are some kind of results we have found after the forming process, and some kind of wrinkles are even came after the during the forming. Okay, some kind of skid lines came during the process. Skid lines are generally the radius given to the upper die, so that this also we can avoid during the process. Okay, and this is actually final component analysis with the scanning. Okay, means after the component being developed, these are scanned, some kind of 3D scanning. Then we have compared according to the actual part and the CAD data. So these are actually some kind of basic parameters where all the dimensions are being checked. And where are some areas where these are some areas where some kind of error found, that also eliminated during the process. So this is actually means part we have taken care in the during the manufacturing, and I hope we have got insight for the sheet metal working in the industry. So this is it, guys, and if you have any questions, then we'll discuss right now.